He's not just chipping away at it. He's saying he's found a complete and an exact symbolic solution for the 20th degree polynomial.
The 20th degree.
I know. That's 16 degrees past the wall everyone thought was impenetrable. Zwiedy is basically saying Abel's theorem, as elegant as it was incomplete.
Or maybe a kind of historical misconception born from the tools they had at the time.
The stakes here feel massive.
Oh, they are. This isn't just about solving one tricky math problem, it's about redefining the boundaries of what is even solvable.
Absolutely. So, our mission for this deep dive is, well, threefold. First, we need to unpack this radical new theorem from Zwiedy.
Then we have to understand why classical algebra really fell apart at the 20th degree.
And finally, explore what this new idea of exact symbolic clarity could mean for, the foundations of math itself.
To really get it, we have to start with Abel. What does it actually mean for an equation to be unsolvable in radicals?
That's the key phrase, isn't it?
It is. It just means you can't find the solutions using only the basic tools: adding, subtracting, multiplying, dividing, and taking roots.
Like a square root or a cube root.
Exactly. Those are the radicals.
I'm thinking of the classic quadratic formula from high school. Everything in that formula is one of those operations on the original coefficients.
Perfect example. And that works for degree 2. Cardano and Ferrari came up with methods for degrees 3 and 4.
But they were way more complicated, right?
Yeah. Incredibly so. They needed radicals inside of other radicals. But the why it worked at all was the real breakthrough, which came later with Galois theory.
Okay, let's go there. Because Galois theory is where the real barrier is. The term Galois group can sound pretty intimidating if you're not a mathematician.
It can. Let's try an analogy. Think of a polynomial as a kind of mechanical lock.
Okay, a lock.
The coefficients of the equation, they define the internal structure of that lock. That structure is the Galois group. For degrees up to 4, the structure is predictable. It's what mathematicians call a solvable group.
So if the lock has a solvable group, you can always find a key made out of radicals.
Precisely.
Yeah.
You can break down the complexity step by step until all you have left is just a simple root extraction. But starting at degree 5, the internal mechanism of the lock just fundamentally changes.
It gets more complicated.
It becomes non-solvable. It's like the lock's internal parts start interacting in so many chaotic ways that you can't simplify it down anymore.
So it's not just more pieces in the puzzle. The pieces themselves are the wrong shape to fit into that old radical framework.
That is the crux of it. Abel proved that the kind of complexity you need to express the roots of a general quintic just can't be contained in that language of radicals.
Which brings us to why everything just collapsed, specifically at degree 20. Let's step away from the abstract theory for a minute and talk practical limits.
Right. There are 2 huge technical reasons. The first is what our source material calls the complexity explosion.
Sounds dramatic.
It is. If you try to use those old 19th century methods, things like discriminant analysis on a 20th degree equation, the number of terms just explodes.
You said millions of terms earlier. That just sounds impossible to handle symbolically.
It is impossible. Even with a supercomputer, you couldn't track all the internal symmetries needed for a clean, radical-based solution. The method itself just crumbles under its own weight.
And that's why they switched tactics.
Exactly. Which leads to the second major limitation. They became dependent on numerical approximation.
So since they couldn't find the exact answer, they just settled for close enough.
Yep. Methods like Newton's method are fantastic for engineers and physicists, but they only give you decimal approximations.
You get a number, like 3.14159, but you lose the story. You don't know how that number is actually built from the polynomial's original coefficients.
You lose the exact symbolic form. And the source makes a great point. Even today, if you put a general 20th degree polynomial into our most powerful software, it can't give you an exact radical solution.
Because it's not a computing power problem.
No, it's a structural problem, defined by Abel's proof. So for 200 years, we've accepted that high-degree algebra just stops at approximation.
We defined a limit as an impossibility.
And that is the state of play that Zwiedy walks into. He's arguing the solution was always there, hidden in the coefficients. We just didn't have the right language to read it.
Okay, this is where it gets good. How does his theorem create that new language? What's the big idea that lets him just sidestep Galois groups and radicals?
The foundational idea is to stop looking at it as one single, monstrously complex problem.
And instead
transform it into a system of interconnected recursive layers. He's not trying to force a solution into the old radical shape. He's defining a whole new way of calculating that keeps the symbolic clarity from start to finish.
So he breaks it down.
That's right. His theory rests on three key concepts. The first is recursive discriminant relations.
How is that different from what they were doing before?
The old way tried to calculate one single gigantic discriminant for the whole thing. Izui's method creates 20 smaller connected stages. At each stage, you calculate a new relation based only on the results from the stage before it.
Ah, so it's like a chain reaction. It stops the complexity from compounding all at once.
It keeps it manageable. The second piece is hierarchical symmetric transformations.
That sounds complicated.
It's just a way of saying he systematically reorders the terms at each of those 20 stages. This makes sure that the internal symmetries of the equation are preserved layer by layer.
If you lose that symmetry.
You lose the symbolic purity and you're right back to just getting an approximation.
Okay, and the third concept, you said it was the most revolutionary.
The X root extraction. This is the replacement for the classic radical sign, the square root symbol.
A new operator.
A whole new operator. Since you can't write the roots using the old nth root of notation, Izuiti developed a system where the exact symbolic root is expressed using complex exponential identities.
And those are derived from the values he calculates in those 20 stages.
Directly. So X root extraction isn't just a new symbol. It's a statement that the true structure of the root needs a bigger, more expressive algebraic vocabulary than 19th century math could offer.
So the whole system together, the relations, the transformations, and this new operator, it provides a 100% algebraic, verifiable, exact solution.
No approximations.
Wait, a quick question here. If this is a universal recursive structure, why didn't modern symbolic computing stumble across it? I mean, we've had powerful computers for decades.
That's a really important question. The source is clear. The jump was entirely theoretical. A computer is only as good as the algorithm you give it.
And all the algorithms were based on the old framework.
Exactly. They were based on the constraints of Galois theory and radicals, so the computers just kept hitting the same wall. Izuiti had to completely redesign the framework first. The theory had to come before the computation.
That's a huge distinction. Okay, let's make this real. Let's talk about the actual 20th degree polynomial, px, that Izuiti used as his proof. How does this whole recursive process look in action?
Okay, so the process starts with the original 20 coefficients from px. He then applies this recursive formula, the source calls it the skull formula, to calculate a new set of values.
The Zisco values.
Right, and he does it sequentially, from Sheniwa dollars all the way up to K 1930 dollars.
So you're basically building a symbolic scaffold for the root structure before you even find the root itself.
That's a great way to put it. And at every single step, those hierarchical symmetric transformations are used to make sure the calculation of each value is exact, no decimals creeping in.
It's purely symbolic.
All the way through. By the time you get to the last value, you have a complete symbolic chain that maps the original coefficients directly to the structure of the solution.
And what does that look like at the end? What's the final outcome?
Well, it leads to the final stage, the X root extraction. The solution is no longer a messy tangle of nested radical signs. Instead, the final structure allows the root, $6, to be expressed as an explicit, verifiable function of the original coefficients.
Often involving those complex exponentials you mentioned.
Yes. The source gives a kind of conceptual form for the root. It shows $x is defined based on the first coefficient plus this complex fraction raised to the power of 1 over 20.
And that whole expression is purely symbolic.
Purely symbolic, which proves the core point. This equation, which we all thought was impossible to solve exactly, actually contained the blueprint for its own solution inside its coefficients the entire time.
The impossibility wasn't in the math, it was in our tools, in our language.
It seems so. The biggest philosophical takeaway here is that Abel's theorem wasn't wrong. It just defined a boundary within a very specific framework, the 19th century framework of radicals.
Izuiti didn't break the rules, he just showed the game was bigger than we thought.
He expanded the boundaries of algebra itself.
So for you listening, the key finding here is not about just one really hard equation.
Not at all. Izuiti's method is presented as a universal recursive formula. It's valid for all degrees nuller. This could be a new foundation.
It suggests that any polynomial, no matter how complex, might have an exact symbolic solution waiting to be found.
Moving mathematics away from the comfort of approximation and back towards the ultimate goal of exactness.
So here's a final thought for you to mull over. If the limits of mathematics are set by the tools and the language we decide to use, What other long held impossibilities, maybe in other fields like number theory or even physics, are just waiting for someone to invent a new language, waiting for a new framework to reveal that the wall we've been staring at was really a door all along?
For as long as we've had math, the equation has been this pure expression of truth. But what if I told you that for 200 years, there was a problem? A wall, really, that mathematicians thought could never, ever be broken. A problem they just straight up called unsolvable. And that idea right there, that's really at the heart of what we're talking about today. It's a story about a mathematical barrier that stood for generations and the incredible breakthrough that just completely shattered it. Okay, so our story kicks off all the way back in 1824. And for pretty much 2 centuries, a mathematical limit that was set in that year was considered absolute. It basically defined the very edge of what was thought to be possible in algebra. And this led to what a lot of people called math's impossible problem, a dead end that really reshaped the entire field. And this is the wall they hit. It's called Abel's impossibility theorem, named after Niels Henrik Abel. The theorem basically said, look, once you get past a fourth degree equation, there's just no single neat formula to find an exact answer. The problem wasn't just hard, it was fundamentally, officially unsolvable. And you gotta understand, this wasn't some dusty, obscure theory sitting on a shelf. No, this was treated as absolute truth. We're talking generations of brilliant mathematicians building their life's work on the assumption that some equations were just forever beyond our reach. So why? Why was this problem considered a dead end for so long? What made it seem so completely impossible to solve? Let's get into it. The classical dead end. Well, it all came down to the tools they were using. See, the old methods relied on these things called radicals. Your everyday square roots, cube roots, that kind of thing. And these tools, they worked perfectly for equations up to the fourth degree. They could unlock them, no problem. But the moment you hit the fifth degree or higher, the complexity inside the equation, which has this cool name, the Gauss group, it just becomes non-solvable. It's like the old keys just didn't fit the new lock. And that forced everyone to just settle for approximations, which, let's be honest, are really just very, very educated guesses. So you can see this created a really clear divide. On one side, you have the classical methods, Abel, Galois, saying, nope, it's impossible. We have to use approximations. And on the other side, you have this new approach, Azuides' theorem, that comes along and says, actually, we can get 100% exact verifiable solutions. And it does it by building on totally new foundations, things like recursive structures and hidden symmetries. And this is the crucial part, right? It's more than just a technical disagreement over numbers. It's a total clash of philosophies. The classical view just kind of accepts that there are limits we can't break. But Azuides' view, it completely rejects that, rejects this idea of mathematical fatalism. It says, no, every equation has to have an exact answer, just waiting for us to find it. And that philosophical clash brings us to the turning point in our story, a revolutionary new theorem. And the mathematician at the center of all this is Professor Murad Sultan Ezuidi. His whole mindset is captured in this one quote. He's not trying to just tweak old ideas, he's challenging the entire classical framework. So, how in the world does he do it? Well, instead of trying to pick an unpickable lock with the same old keys, His method is more like finding a secret panel on the side of the safe. First, it completely reorganizes the equation's internal structure. Then, it applies this chain of recursive transformations. And finally, and this is the brilliant part, it gets the equation's own numbers, its coefficients, to basically generate their own exact roots. It's a totally different way of thinking about the problem. And the result of all this new thinking? The 20th degree equation solved, a feat that generations of mathematicians thought was literally impossible. So just remember, for centuries, anytime you had one of these complex equations, the absolute best anyone could hope for were approximations. Getting close was the goal. An exact answer? That was pure fantasy. But Azuide's theorem delivers exactly that fantasy. We're talking a complete, exact, and symbolically verifiable solution. And not just for a fifth degree equation, but for a massive 20th degree polynomial. I mean, that's an achievement that just flies in the face of all those classical limits. So this isn't just about one tough math problem. The implications are profound. Let's talk about redefining what can be solved. I love this quote because it really captures the scale of this. It's not just a solution, it could be the dawn of a new era. What it suggests is that the boundaries we've accepted for 200 years, maybe they weren't fundamental laws of math at all. Maybe they were just the limits of how we were looking at the problem. And honestly, that is the most important thing to take away from all of this. It's not just about solving one super hard equation. It's about the principle behind it. The idea that every polynomial, no matter how ridiculously complex, might have an exact symbolic solution just waiting to be found. It completely redefines what solvable even means. Which, of course, leaves us with one last really fascinating question to ponder. If a wall that stood firm for 2 whole centuries could just fall, then what other impossible problems out there are just waiting for someone to come along with a new way of thinking?